Alright, good morning everyone. I'm Richárd Forster. I'm a PhD student here at Budapest Egyetlen University and working at CERN as a doctoral student and the collaboration spotting team. And I'm responsible for making this whole thing running very fast and very efficient as possible, because as Xavier was telling, it is a graph visualization tool that is supposed to be interactive. So whenever you are seeing something, you are supposed to be able to interact with it, click on it, recompute it, and do it as many times as you want and as fast as you are capable to do it. And as Xavier was mentioning, we have some interest from Wigner. We have some projects that are linked to the project as a very valuable asset to visualize their own data. But on the other side, we were also looking for some partners to be able to compute it very fast, and it was a very comfortable thing to have something in Budapest that they have the GPU laboratory, that they can provide some resources for us so we can test our approach on some very bigger machines than what we have at hand at CERN. So what I would like to talk about is just a little bit about the graph generation, what we would like to have to be able to start the computation at all. Then the community detection that we are using for detecting the communities without knowing anything about them beforehand. For that we are using the Louvain algorithm. Then I will talk a little bit about the force atlas that we are using for the force-directed layouts. That is the most tricky part, I think, as it has the most problems for Xavier. Then I will talk about our performances, and let's see a little bit about the future work. So the graph generation. So to be able to start the computation, we need the nodes and the edges, of course, to be able to create the graph. But to have those nodes and those edges, we will need the collaborations first. And those collaborations will come from the database at first. We have made some preparations to be able to cache them, so we will not always relying on the database, especially if we have multiple users at the same time. We would like to request maybe many different data sets, but maybe if they are trying to access the same kind of data, they will be very lucky that the first person will have to wait maybe some minutes, and then they will be able to retrieve the data right away. So for some numbers, you can see that I have 4 graphs. All of them are searches for technology, silicon database, 3D and CT, which means that this was the keyword that I was searching for in title and abstract in papers. So in these cases, you can see that for the collaborations, for example, in the silicon, it can take 33 seconds, and this is because we are trying to get it from the databases first. This is all the numbers are from the database. We are not getting from cache anything. And after the collaborations are downloaded from the database, you can see that the nodes are usually generated in less than a second and the edges less than 2. And we will see that these graphs have hundreds of thousands of nodes and even more edges at some time. So what about the community detection? We are using the Louvain algorithm that is supposed to be able to tell us what kind of communities we have in our graph. We can use it for real networks, so that means that if you download some data from, I don't know, maybe from YouTube, you get the user data, then you will be able to tell that which users are checking on each other videos, for example. And this algorithm is inherently sequential, which means that you will have to check all the possible neighbors. You are checking which community is better than the other. So it's not very easy to parallelize it at first, so there are some parallel heuristics that can be applied, and we are using those to parallelize the whole process. So the Louvain method is a multi-phase iterative greedy algorithm, and this means that for the very first part you have your nodes, and you will tell that these nodes are actually the communities, which will mean that if you have n nodes, you will have n communities at the beginning. And then you will start to check the connections, what kind of nodes they are connected to. And we take into account the weight of the edges they are connected with. So if you have multiple neighbors that are multiple communities at the beginning, then you will check which are the modularities that are the biggest. The modularity is computed based on the degree of the node and the weight of the edge. And if you find the biggest change, then you go to that community that gives you the better modularity. And we go until we reach a certain threshold that will tell it, okay, there's no much more change in this graph, so we will not try to change anything else because it will be useless. And this modularity will always monotonically increasing, and as I said, it is inherently sequential. So to make it parallel, we are applying two things. First, the singlet minimum label heuristic, and then the generalized minimum label heuristic. So what are these? The singlet minimum label heuristic is a very simple thing. This only means that if you have two nodes that are connected with each other, then you will not have to compute too much. You just check that which community is the lower in the label. They are labeled from 0 to n-1. So in this example, if for the node I, the community label is 1, for j it's 2, they are connected, so which one will go to the other community? It will be 2 because we are 2 to the 1 because we are always moving to the community that has the lowest community label. And to make it more generic, because you will have a lot of graphs that doesn't have only nodes that are connected to only one other one. So in this case, you will get the minimum. I always try to get the minimum label, and it will mean that in this case, for example, yeah, we would like to check where would the node label the I go in which community, and it will say that it will go to the community of K because it is the lowest from its neighbors. And we will always do the same. We will check the other nodes from the neighbors. We will see which communities they are belonging to, which communities are belonging, in which community the neighbors are belonging to. These communities will have their own weights, and after we are progressing, we will see that we will always move to communities that have the bigger weights, and these weights will be effectively computed by the weights of the edges, and it will be the sum of the weights of those edges that connects the nodes that are inside the community. And a small example that you have multiple nodes, and those that are belonging to the same community will have the same color on the graph. So for the layout, we are using the force-directed layout that is effectively an n-body simulation, which means that it is running the repulsion and the attraction parts. It makes the visual interpretation easier. The computation may be not better because you will have a lot of things to optimize in it. And it depends what you like to see, because on smaller graphs it works very fine, on bigger graphs it's very hard to do it efficiently, so we have some tricks to apply in it. And the result also seems to depend on the starting state. So to parallelize it, of course, we can parallelize the repulsion and the attraction, and as Xavier was saying that in default case right now, in the system the repulsion runs in such a way that it checks all the nodes. So you would get one node, it will check all the closer nodes to it, and if it will check if it is possible that it will overlap. If it will overlap, then it will start to repulse each other, and it has an n-square time, so it's very not efficient. There are some optimization techniques for that, and one that is easy to apply, and in this case I have applied it and the numbers are running with that applied, is the Parts-Hut algorithm that builds up a quadratic tree that gives you regions that the nodes are belonging to, which means that you will not need to check all the nodes at every time, but you will have the regions that needs to be checked. So if you check one node and it belongs to one region, then you will have to check the region that is surrounding it. And if you push one region, you are pushing all the nodes that are inside that region. So it will make the whole algorithm run only through n times log n time, which will be much faster compared to the n-squared one. And after you are repulsing, of course, you have the attraction power, because those nodes that are connected by the edges, they will be repulsed based on the weight of the edges. And this can be parallelized easily. And this attraction can be somewhat parameterized by the user. By default, as the algorithm was made in its original form. But there's a small problem with it, because if you have, for example, you can change how much the weight is taken into account in the computation. And the problem is that the user can tell that, okay, I would like to take the weight, I would like to take the square of the weight, or I would like to take whatever power I would like to. And if you have very big weights and you will say that I would like it to the power to 10, it is possible that you will have such big numbers in there that you will overflow, and then the whole computation will just give you false information. So these layouts are very big, I know. So in the original layout on the left one, it is just running the original algorithm. On the right side, it is based on the communities, which means that Forster Plus has been computed of all the communities. And then it was done on the whole graph. So as you can see here, you have communities connected together. They are put into their own layout. Then you have these communities, and it is computed as a whole. So you will have a Forster Plus layout computed on a graph that has the nodes of the communities itself and not the real nodes. So in this example, it's not so clear, but it can give you much better results than the original. So about the performances, as I was showing before, there are three graphs, the 3D, the CT database, and Silicon Technologies. Everything is implemented in C++. The GPU version is implemented in CUDA. On CPU, it was running on 8 threads. We were running on the GPU laboratory machine, that is a Core i7-920 and the GeForce GTX 980. It was using only one single GPU. And for the community detection, we can reach up to 12 times faster runtime. In this case, the CT is the biggest graph, and it also achieves the highest speed up on the GPU. I think it is also important to mention that just because you have many edges and many nodes, it doesn't mean that you will compute fast or slow, because it will also depend on the layout, on the structure of the graph. Because if you will have, for example, n nodes and 2 will be connected all the time, so you will have only half as many edges, and you will have a case where I was showing a single minimum heuristic that you have 2 nodes connected to each other but nothing else. Then it will mean for the community detection that in one step it can reduce everything. You will have half as many communities at the end, how many nodes you had originally, and it will be finished. So this highly depends on the structure of the main graph. So you can see that, for example, on the CT graph, it was taking 18 seconds on the CPU and only just 1.5 on the GPU. And for the Forster-less layouts, we could reach up to 9.8 times faster runtime. Also on the CT graph, it took more than a minute on the CPU and just 6.5 seconds on the GPU. So there's a lot to gain using GPUs compared to the CPUs. So for the future work, of course, we can always optimize how the data is retrieved. We can retrieve from the database, that's fine, but also how it is computed and put into a graph itself to get the nodes and the edges. It can be also optimized a little bit better, because also it's okay that it takes less than a second to generate the graph, but if you will have hundreds of thousands of users, for example, it can take some time. So maybe we will need to optimize it further. And also for the Forster class, as Xavier was also mentioning, we should apply the Barsut algorithm, see what it does in real world graphs, and further optimize the performance, because maybe we can still find some better solutions that will also run better on the CPUs and not just only on the GPUs. And I'm also working now on a better implementation that is really a lot faster also on the CPU and also on the GPU. So there's still some things to do on the optimization side on both parts, even on the community detection and the layout too. And thank you for your attention.
Thank you very much for that talk. Questions?
Just okay. So So the question is that have you ever considered to put your CUDA code into OpenCL one?
No, not really.
Just back we had some kind of experience that if we put the code to OpenCL and try to run it on CPU, it will give you better performance as well.
Yeah, that's something that we should also apply.
Just to consider.
Yeah.
That's it.
I'm just curious, at the very beginning, the bottleneck is building stuff from the database. What is the absolute lower theoretical minimum time you must spend on just reading through all the data from which you need to get groups?
Well, if you would like,
If you're not in cache.
if you would like to get everything,
No, I mean, you won't get everything. Presumably, you build and draw as you build, but buy most of it.
well, to build, you have to draw everything that you need. And if you will need a graph that will take a million nodes,
No, but in that example, so you had an example which said like you have to do something 30, 40 seconds.
Yes.
Right? I was just curious because some part of it is probably CPU and.
no, this is just the database.
This is
that part
just,
is
just
just
a pure
the-
access time.
Yes.
Ah, okay, great.
But also there's some network time too because the database is running in another machine.
Yeah, sure. But that's what I understood. Yeah, that's what I was asking. So it's not the time to find these things. It's really to get the data to the data and back. Which drives
Well,
the
it depends on the database. Because it will take some time for the database to fetch the data because it also applies some caching. But if you are trying to get some data that was not retrieved for some time and it is not in the memory anymore, it will try to fetch it from a hard disk or SSD or wherever it is stored, and then it will also take some time.
But you're not asking the database to return you clusters.
No, I'm asking the database just to return the nodes.
And that took you 30, 40 seconds.
Yes.
Oh, okay, good. I misunderstood.
Okay, so thanks to the speaker again.